Good afternoon, everybody. So our first and last speaker for this afternoon session is David Alfaya, and he is going to speak on automorphism group of the moduli space of parabolic bundles.
Thank you very much, Sanjay. First of all, I would like to thank the organizers for inviting me. It's a pleasure to be here and be able to give this talk. Also mention that this is a joint work with my advisor, Tomás Gómez. So before getting to the geometry of the moduli space and computing the automorphism, let's start by reviewing a little bit what a parabolic vector bundle is. So a parabolic vector bundle is a vector bundle E over X. X is a smooth complex projective curve, Riemann surface, the set of mark points, a finite set, D. And over each mark point, we're going to enhance this vector bundle with a filtration by linear subspaces of the fiber. And these linear subspaces are going to be given weights, real weights, alpha 1 to alpha L, between 0 and 1. The geometry behind this is the following. On one hand, this is the natural structure that appears if you want to get a correspondence, kind of Narasimha-Sassari correspondence between the modular space of some objects remaining of vector bundles and representations, unit representation of the fundamental group. On the other hand, these kind of structures are useful if you want to consider some Higgs bundle or connection with a singularity, with a logarithmic singularity. The idea behind it is that the filtration will somehow measure the directions in which the sections of the connection or Higgs bundle diverge, and the alphas are going to measure the speed of that divergence. But let's forget for the moment about Higgs bundles and connections, just get the underlying structure, and well, if this flag is complete, then we say this, it's a full flag. Instead of thinking about filtrations of the fiber, we could alternatively think of filtrations by subshifts. So if we are given a filtration by linear spaces of the fiber X, then we can relate it with this sequence, and for each fiber, we can consider the subshift of Ex over I that fits into this sequence. And well, this seems to be useful because we can provide another codification of this structure that fits together the weights and the filtrations if we think about left continuous filtration parameterized by real values. So what's the point here? We are going to give for each parabolic point X and for each value alpha a set of filtrations E alpha X indexed by a real number that satisfies these four properties. First, the filtrations are going to be decreasing. Second, they are going to be left continuous. That means that if we fix some alpha, then you've got left continuity of this filtration. And then we got this periodicity condition that essentially tells us that all these shifts differ only at the point X, and also that the whole filtration is defined if we know what happens between 0 and 1. And finally, the basis of this filtration, the basic vector bundle on which we are constructing the parabolic structure, would be just the 0th step of the continuous filtration. In other ways, if we have the values alpha I and we have the steps EXI, then we can construct this continuous filtration just by taking the quotients. And if we have the continuous filtration, then the alpha I are the jumps. Instead of looking at this, we can see it more visually with a picture. So say that we have our vector bundle E, and we have a real parameter alpha. So what we're doing is, for each value of alpha, we're giving a subshift of E, at least for positive alpha, such that they form a left continuous filtration, and the value at alpha plus 1 is just the value at alpha tensor by O of minus x. If you consider this kind of structure, then it is clear that you can distinguish the jumps. So the jumps are the parabolic weights. And the values of this filtration gives you the steps in the usual construction of usual notion of parabolic bundles. In order to get a modular space, we need to define some stability on these objects. And it will be some kind of perturbation of the usual notion of stability for vector bundles. Usually, we have a notion of degree. And here, what we are doing is defining the parabolic degree of one such structure as the degree plus the sum of the alphas counted with multiplicity. If we do that, we can define the parabolic slope, as usual, quotienting the degree by the rank. And we define, we say that a parabolic vector bundle is semi-stable if for every sub-bundle with the induced parabolic structure, we get the usual inequality between the slopes. Here, with induced parabolic structure, I mean this stuff. If I get a sub-bundle F, then by intersecting with the filtration, I get a filtration for F. And I just get the corresponding weights, like the maximal weights I can get that fit the filtration. With this structure, I can construct the modular space. But there's some problem. This modular space, if I don't say anything about the weights, I must distinguish between semi-stability and stability, as with the usual vector bundles. And this is an issue, for example, for considering smoothness of the moduli. This modular space, if I construct it for any weights, it will not always be smooth. So what I can do is I can restrict myself to some kind of alphas, some kind of parameters that I'm going to call generic. This is the expression, doesn't matter really much. The important thing is that if I get a generic, in the algebraic sense, a generic weight, then there are not going to be any strictly semi-stable parabolic vector bundles. Just because by a numerical argument, if there existed some strictly semi-stable bundle, then if I write the equation, then I can write the Segre invariant of f and e in terms of the alphas. And if the alphas just don't add to be an integer for any possible combination or selection of the alphas of the subbundle, then this is not possible. So the conclusion is we have some generic weights for which there cannot be any strictly semi-stable parabolic vector bundle. And for that generic weights, what happens is that the modular space, and it's for full flag, and the modular space is always smooth. And for full flag parabolic weights, which are generic, then Boden and Yokogawa proved that it's not only smooth, but it's a smooth rational variety. And moreover, the modular space is fine. That means that we have a universal parabolic vector bundle over the modular space. That's a good improvement from the usual modular space of vector bundles, in which we need to restrict to coprimality conditions in order to get some universal bundle. Here, you just have to force full flag, and even not full flag, just full flag at some of the point. It's even weaker. The result by the Boden and Yokogawa is much stronger than this, in order to get a universal bundle. Now that we know the modular space, we can ask some questions about it. I'm going to focus on the classification of the isomorphism classes of these spaces. So the first question is, what can we say about the symmetries of this space? If we fix the rank, the system of weights alpha, and the determinant, then what can we say about the symmetries? Moreover, once we have solved this question, then we can ask what happens if we change the parameters. If we change the curve, the rank, the weights, and the determinant, can we determine whether these two modular spaces are isomorphic or not? What can we say about it? And finally, if we know that they are isomorphic, can we describe the isomorphisms explicitly? Or they are just going to be, this is some PR, this is another PR, then we know that they are isomorphic. Can we say that there's an intrinsic way to define these isomorphisms? In the compact case, we have some results. The first one is the well-known Torelli Theorem. If the modular spaces of vector bundles, stable vector bundles over a curve are isomorphic, then the curves are isomorphic themselves. This is a result by Mumford and Houston in '68, and then this was done for some cases, and the general result from Narasimhan Ramanan. And more recently, we could answer the first question, in fact, what are the automorphisms of this space. This was first done by Kubidakis and Pantev. There's also a similar result, a reproof of this argument by Juan Ramanan, and later Biswas, Gomez, and Munoz in 2013 gave a different proof of this, which was also valid for symplectic bundles. The result is the following. We can define these basic transformations, 3 basic transformations for vector bundles that are pretty natural. If I get a vector bundle E, then we can just take some automorphism of the curve, some line bundle, and given the vector bundle, we can do the following thing. We can first take the pullback by it, and then tensorize by some line bundle, or we can first take the dual, and then take the line bundle. And it is clear that these operations don't change the stability of the underlying vector bundle. So, as we can do this clearly over families, and they don't change the stability condition, this gives you automorphisms. This is pretty clear. So the theorem is, there's nothing else. These are the automorphisms of the model space in the compact case. So now we wonder, first, there's a problem here. I said that all these things give you morphisms, but there's a restriction. This would give us morphisms if we were considering the union of all the model spaces of every degree. But we are fixing the determinant. And it is clear that if we apply these transformations, we change the determinant of the underlying vector bundle. So what happens is that we need to restrict ourselves to combinations of those transformations that actually preserve the determinant. This gives you some little equation over the choices of the automorphism and the line bundle. And whenever that is accomplished, the equation itself doesn't matter, it's just some topological restriction. Then we are done. And in fact, it is not really as, once you have fixed the degree, then fixing the determinant is not pretty much of an issue, because you can always get a square root, an earth root of some line bundle. So the problem here is splitting the degree. In particular, excuse me? Sorry, can't, you need? Yeah. There are some. Here I'm not. This is I think for genus at least 3 or 2 with higher rank. Maybe Indranil can tell it. I think this is for genus at least 3 and rank. This is at least for genus 2, I think, in the version of Nassim and Ramanan. So this, for example, this doesn't make sense for genus 1. For it, this doesn't make sense. And then, in particular, what happens is that the dual only appears if there's some numerical condition on the rank and degree. You don't always get combinations of all 3 types. There are restrictions. So now, what can we say about the parabolic case? So first of all, we've got 3 natural transformations that we want to extend. So we can do it in the natural way. If we have a parabolic vector bundle and we have an automorphism of the curve which fixes the set of parabolic points, now I'm saying that it fixes the divisor, not each point. That means that we allow this automorphism to permute the points, okay? Then we can take the pullback, and this is clearly another parabolic vector bundle. If we have a line bundle, we can tensor. And we can also use the parabolic dual, defined this way. If you don't want to use this interpretation, which if you're not familiar with this left continuous structure, then it might be a little bit stranger for you, then you can just think of it this way. If we have filtration by then what we can do is, if we dualize, we can dualize all of them. Then you get quotients. And then we can take kernels of them, and then it gives you a filtration. Right? So that's essentially what happens in the quasi-parabolic structure, if we forget about the weights. At least if these weights are not zero. And well, at some point, we tensor by O of minus d for some reasons, some good reasons. But this is essentially the kind of thing that is happening. So now the problem is that, as we saw previously, these transformations in the compact case change the determinant. So if we want to get an automorphism, we must take combinations of them that get, again, the same determinant. But here there's another problem, that when you do these transformations, they do not only change the determinant, but they also change the weights of the filtration in the following way. If we take the pullback, then if this automorphism permuted the points, then the induced weights are permuted. So we're not, if we consider the modular space with fixed weight alpha, then this is not in the same modular space. We have to change the weights. Similarly, if we take the dual, then the weights are just inverted. This has weight alpha 1, alpha 2, alpha r. Then when we invert this filtration, we get weights 1 minus alpha r, y minus alpha r minus 1, to 1 minus alpha 1. But, well, before engaging into questions about how do we manage to make combinations of these that actually fit the determinant and the weights, we can ask ourselves, is there something else? These three transformations clearly come from automorphisms of the modular space of vector bundles. Is there anything else that we can do on families of parabolic vector bundles? And the answer is yes. We can make Heckle transformations. We call that the Heckle transformation is the following correspondence. If we start with a vector bundle and we get some linear subspace, then we can define this sequence. We can take the Heckle transformation as the subshift of E, such that when you take the quotient, this quotient is supported at X, and corresponds to the quotient of EX modulo L. In particular, what happens is that if you look at the fiber, when we get EX, the Heckle transform into E, the fiber-wise, this would get into the L subspace. This has been pretty used along the literature a lot. It's a pretty useful tool to make correspondences between modular spaces. And the thing is that in the modular space of vector bundles over the compact curve, we cannot make use of this tool because we have no way of giving an intrinsic sublime bundle over the whole modular space that allows you to do this in families. But if we have a family of parabolic vector bundles, we have a way to choose these sublime bundles over a fiber, the parabolic structure. So then what happens is that we can define the Heckle transformation of a parabolic vector bundle to be the quotient, the Heckle transformation by the different steps of the filtration. So we get R different Heckle transformations at each point. We can combine them. So the question is, okay, I have given you a parabolic vector bundle, and you give me a vector bundle. What's the point? I want a parabolic vector bundle. I want a filtration for this H. So one first try is, okay, I have this sequence. And then if we look at the sequence at the point, then we have something like that. We have HX. This goes into EX. That goes into just EX over X plus 1, 0. And of course, we know that this is exact at here. So in fact, if we call this F, the image of this morphism is just the AX L plus 1 here, right? So then what we can do is, well, we know that this is a vector bundle, and we have this step of the filtration. All the next steps are preserved, right? So if this gets into here, and this gets filtration by the remaining steps, then we can give these filtrations here, just taking the pre-images. Right? But this doesn't solve the problem, because here, if we started with a rank R filtration, here you only get R minus L points of the filtration. So how do we complete it? And the answer is, well, I have not completed this sequence. Here I have to set the Tor. Here I have the Tor of xl plus 1 of OX. This fits the sequence. So what happens is that when I have finished everything here, I still have an element here which gets inside HX. And of course, here I have 0. And this is actually f minus 1 of 0, because the sequence is exact. So what happens is that when I have exhausted all the possible filtrations here, I can start filtrating this element. And what happens is that this element have a really nice structure. It's just the tensor of Ex of the quotient times some element. And of course, it's just Ex L plus 1 tensor some n. And now I know how to filter this element, because this is filtered. This element is filtered by the filtration quotiented by the element. That means I can take Ax2 over Ex L plus 1 tensor n and continue just as the last element here, which would be Exl over Ex L plus 1 tensor n. And if you do that, you obtain again a full flag filtration of H. So we will call this H with this filtration the Heckle transformation of the parabolic vector bundle E. And we have a choice. We can do this as many times as we do it for each point, and we can do it as many times as we want between 0 and R. So we can define this. Another way of thinking of this, in terms of continuous filtration, is that we can understand this transformation as a kind of rotation of the filtration. Okay, this is pretty clear. We have L elements that were behind. We put it in front, and when we put the other R minus L elements behind them. But we can think it also as a shift. Say that we have a left continuous filtration, okay, the Ex alpha. Remember that they were decreasing as alpha increases. And we get some parameter epsilon, which is greater than the first jump. Okay? Then we can consider the following also left continuous filtration, which is just taking the original filtration and shifting it. We define the alpha element of the new filtration as the element alpha minus epsilon of the old one. So now, if we take the 0 element, that remember, it was the base bundle over which we are defining the filtration, the base element here is just the alpha 2, which is a Heckle transformation. Again, this is just some little computation. Let's see with a picture. So we start with our left continuous filtration, right? Same picture before. We have the E bundle with the filtration, the continuous filtration, right? Indexed by alpha. And now let us select some value epsilon, which is greater than the first jump. In this structure, remember that, recall that what matters for defining the parabolic structure is what happens between 0 and 1. So what we're going to do is we're going to shift this window to epsilon, right? So instead of taking, I don't know if you can see it, but it's here. You can see this window, we can shift it to epsilon. And then what happens is that if you do so, the first element you encounter at epsilon is just the next step of the filtration. This was our H. Okay, this is the E X alpha 2. This is a subshift of E. And then we have the next elements that you encounter. By one periodicity, you get a full flag filtration just by the periodicity condition on the left continuous structure. So now what we can do is just, okay, shift this back to 0. we have a new filtration between epsilon and epsilon plus 1. If we shift back, we change the weights. We have a filtration between 0 and 1. And this is a new parabolic vector bundle that essentially coincides with the structure that we find earlier. And if we do this structure, we can check that it has some very nice properties. First is that it preserves stability. If we give it the induced parabolic weights, that means that if the parabolic vector bundle, the original one, is stable with some weights alpha, then when we apply this transformation, if we give it these shifted weights, then it's also stable for these new weights. It's also clearly cyclic, or at least almost cyclic. If I do this structure, this operation r times, then we end up with the same filtration. You can see it pretty clearly here. If I ended doing this r times, then we will arrive here, and we arrive to e of minus x again. Finally, it is clear that, it is clear that this operation is local. If you do a Heckle transformation at one point, that only changes the stock of the fiber of the vector bundle at that point. So if we do two different transformations at 2 points, then they commute, and we can do whatever we want in 1 point, and it doesn't affect the rest of the bundle. So at the end, what we can define is we can compose several transformations at each of the points, and then the complete transformation is really defined by a divisor. So, well, I'll just skip this. You can also interpret this in terms of a tensor bundle, and a tensor by a parabolic vector bundle, okay? So, by a trivial parabolic vector bundle, but with a non-trivial parabolic structure, but I leave it. So we arrived. Excuse me. This commutes with tensor product by a line bundle. This can be reinterpreted as a tensor product with some special line bundle. So then it obviously commutes with tensoring with other parabolic line bundles. It also has a nice commuting properties with dualization and with pullbacks. In fact, you can precisely compute all the interactions between these 4 transformations. So now, in fact, these 4. So now, let me define these 4 transformations to be the parabolic basic transformations now. And we know that these are well-defined over families. And if we give a vector bundle with weights alpha and determinant chi, which is stable, then we get another vector bundle, which is T of A is stable, T of alpha is stable, which T of alpha is this transformation, doesn't really matter, just have to know that they change it in a natural way, and with a changed determinant, and it preserves stability. So in terms of moduli, what we are saying is that the combinations of the transformations give isomorphisms between the modular space of parabolic vector bundles with weights alpha and determinant chi with modular space of TD of parabolic vector bundles with weights TD alpha and determinant T of chi. And the result, by my advisor and me, is that this is everything there is. Again, these parabolic transformations generate the whole group of symmetries of the modular space of parabolic vector bundles. And that's for genus at least 4 and generic weights, an arbitrary rank. So the problem is now the following. Just as before, when we had the basic transformations on the vector bundle, this changes the determinant. So now, if we want these transformations to generate an automorphism of this modular space, then we have to impose 2 conditions. First, they must preserve the determinant, and second, they must preserve the stability. The first one is really easy. You can make the computations and get an equation, right? It's a topological concern. You have to fix the degree. But the second one is difficult, because you have to see whether 2 parabolic weights lie in the same chamber. So, once we arrive to this point, we have 2 choices. The first is fight against the parabolic chambers, and try to classify precisely when two weights live in the same chamber, or there's an alternative. The thing is that even if these transformations, these four transformations, change the parabolic weights, they lie in they are well defined for quasi-parabolic vector bundles. And even if they change the parabolic chamber, they might change it just a little bit. So, said it in another way, these transformations do not always induce a whole automorphism of the modular space, but they will always induce a birational map between these modular spaces. And this birational map is not any birational map. It's a little bit more special because it's defined over really big sets. Let me make this precise. If we take two varieties, we say that they are k-birational for integer k. If there are two open sets, u and u prime, in the varieties, which are isomorphic, and such that these open subsets are big, in the sense that their codimension is at least k. Let me draw a little picture. What I'm saying here is that I have this x, phi, I have this x prime. So this can be decomposed into, let's get out some divisor set, and let's get the open set U, let's get some divisor here, set prime, not divisor, sorry, it will be just some subspace, some closed space, set prime, and we get the U prime. So what happens is that U is isomorphic to U prime, and then this set and set prime are really small. They have a large codimension. The complement has large codimension. Why is this useful? Well, first, for k equal 1, this is just birationality, useful birationality, nothing new. But for k equal 2, there are some nice properties. For example, the Picard group is invariant under 2 birationality, but not under rationality. Also, by Hartog theorem, the globally defined functions, well, this is under normality assumptions, there are assumptions here, but if the varieties are normal, then if they are 2 birational, their globally defined functions have the same. Also, for higher k, there are lots of topological invariants and cohomology groups, etc., that are well defined and are, as an invariant for k birationality, but they are not defined for lower k birationality. So at the end of the day, we obtain, it's interesting to understand what happens with the birational class of some variety. And in our case, well, for k equal 1, there's nothing really interesting. Boden and Yokogawa, well, there is, but it's older. Boden and Yokogawa already proved that this variety is rational. So the one birational class of the modular space for every curve, for every alpha, for everything, is just Pn. Is that, yeah, so the automorphism group, the one birational automorphisms, are just the Cremona group. But for k equal 2, there's a surprise. If we consider 2 birational, then for genus at least 8 and generic full flag, what happens is that the 2 birational automorphisms are precisely the compositions of basic transformations that preserve the determinant. So now we forget about stability completely. And the thing is that for this genus, the wall crossings are in codimension 2. So we can completely cross away all the barriers, all the geometrical barriers in the stability chambers. And then for G greater or equal than 8, these automorphisms are everything that you can define that is a 2 birational map. And so between these two things, what we prove is that we can classify the automorphisms. All of them are pullback, tensorialization, dualization, and Heckle. And if we restrict to 2 birational, then we know that all of these generate an automorphism. If we are in the isomorphism class, then some of them will, some of them not. We have to classify afterwards. Then we can address the second question, whether they are isomorphic. And the typical way would be to wonder about a Torelli type theorem. So for rank 2, this theorem was proven by Balaji, Del Bagno, and Biswas. in 2001, if we have genus at least 2 and this condition for the weights, we have to have small weights in the sense that they are small enough so that the parabolic stability and the stability and derivative are the same. And rank 2, then if the model spaces are the same, then the curves are isomorphic. And this means that you get an isomorphism such that sigma of d equal d. Sorry. But we get it for the original result was for small weights and rank 2. Later on, Sebastian, in 2010, took into account that the same proof that was available for rank 2 could be applied for arbitrary rank, but with the restriction that the weights would be of rank 2. That means that you have the rank R element, but at the end of the day, what you have is a two-step filtration in which the first step is just an upper plane. So at the end, it's essentially this proof is applying the same proof, just changing the rank. But at the end, the restriction was there. You have a restriction on the ways that you can consider. And what we prove, and here I have to mention also thanks to Fernando Basu for some useful discussions about this theorem, is that if the genus at least 4, then for arbitrary generic weights full flag and rank R, if the modular spaces are isomorphic, then the variety is isomorphic and you also recover the ranks. Moreover, we can address the same question in the k-birational category. So, of course, for k equal 1, this Torelli type theorem doesn't make sense because you know that by Boden-Yokogawa result, for k equal 1, you know that this modular space is rational. So all the modular spaces, independently of the curve, the weights, they are isomorphic to Pn for some n. So the only thing that matters is the dimension. They are indistinguishable. But here comes the surprise. For k equal 2, then we can do better. And in fact, we can recover a reciprocal of Torelli theorem. If we have genus at least 8, and we have generic full flag weights of rank R, arbitrary rank, then, and also arbitrary degree, here I forgot the Torelli theorem, yes, it was for every degree, no coprimality conditions either. So if the two modular spaces are 2 birational, then we know that the curves are the same and the ranks are the same, but also we know the reciprocal. In the 2 birational case, these modular spaces are 2 birational if and only if the ranks are the same and the weights are the same, the curves are the same. You don't mind about the weights, nor the degrees of the bundles, nor the determinant. So, second question solved. We know that if these two are isomorphic, then, or at least partially solved. These two are isomorphic if we do these two are isomorphic, then you have the same curve. And in the 2 birational case, this is completely already done. We have this equivalence. So now it's the last part of these questions. Is okay. I know that if they are isomorphic, the curves are the same, but what happens about the parameters? How does it change? And also, when they are isomorphic, can it really characterize the isomorphism? And the answer is yes. We can characterize precisely which isomorphisms there are. And they are all not natural transformations, they are basic transformations. More precisely, if we have an isomorphism from a modular space to another of parallel vector bundles, then there's some isomorphism between the varieties, and there's some basic transformation such that the following thing happens. I'm going to write it this way. Here, the Heckle is not necessary anymore. So, if I have M, X, R, alpha, I, and I have automorphism phi, M, X prime, R prime, alpha prime, chi prime, what happens is that this morphism factorizes into, first, there's a natural transformation, a composition of natural transformations, T, that is going to be of this type. P of E dot is going to be just as that kind of stuff. Then the pullback of some Heckle correspondence over some diversion of E dot, tensor by same lambda, or the pullback of this Heckle correspondence of the G of this bundle. That's also a bundle. So it's one of these two types. And this arrives to some modular space where X with the same R with a different TD alpha and a different T of chi, right? And then these two must be related by the pullback by some other tau. Here it's called sigma. I might change this. So it's the same notation, sigma, the same point of root tau. Okay. So this sigma goes from X to X prime and sends D to D prime. And then, so that this alpha prime goes to pullback of alpha prime, and chi prime goes to pullback of chi prime, right? And with this should go this way in this it's irrelevant. It's an automorphism. And what happens is that this commutes, but it commutes not as invariant. That means we're saying that T of chi, this must be equal to the pullback of chi prime, but we are not saying that T of alpha should be equal to the pullback of alpha prime. Instead, what we are saying is that these two must be in the same parabolic chamber. So the isomorphisms are precisely natural transformations composed with some pullback, such that they send the determinant to the other determinant and alpha stable vector bundles to alpha prime stable vector bundles. Here, of course, is the same problem as before. Either we characterize when does this happen, or we can go to the 2-birational category. And in the 2-birational category, we have a similar result. Two modular spaces are 2-birational if and only if, this is working, if and only if there is an isomorphism and a diagram like that, such that now this condition doesn't matter, such that the determinants are compatible. It says one to the other. So we get the result. We get the full picture, or at least almost full picture. There's something else here. First, we have classified. If we have an automorphism, then it's a basic transformation. And more generally, if two modular spaces are isomorphic, then this isomorphism is essentially some basic transformation, up to displacing the modular space by some isomorphism between curves. And if the two are isomorphic, then of course the curves are isomorphic. So the only thing left to do is to answer this thing here. That means this thing here. In other words, we have all the way down here, we have worried about whether two parabolic weights lie in the same chamber after doing one of these transformations. And the thing left to be solved is when do these weights really land in the same chamber. And the idea is to go through the Moduli theory from the point of view not of parabolic vector bundles, that means these weighted flag structures of the points, but of quasi-parabolic vector bundles plus a stability condition. So fixing the parabolic weights for our moduli is the same as fixing a stability chamber, really. And given this modula is just the model space of alpha stable quasi-parabolic vector bundle. So what I'm going to do is I'm going to get rid of these fixed weights, and instead I'm going to substitute this fixed weight notion by a stability notion. And then the goal is to characterize whether one transformation, one composition of this transformation of these transformations preserve or not some stability chamber. So, in particular, we need to characterize the geometrical barriers of this chamber. In this work, in this presentation, I'm going to focus on the high genus situation, so that these chambers will be characterized numerically. And I'm going to address what happens otherwise. So, if the genus is high enough, we can make use of brilliant theory and the results on the stratification of the model space of parabolic vector bundles by the Segre invariant given by Bose and Biswas. And if the genus is high, then what happens is that given two different ways, I can use this theory to find some alpha stable, beta unstable parabolic vector bundle that breaks, that geometrizes the existing barrier between these two weights. I'm going to paint briefly this stuff. Wait a this. So say we consider the set of possible alphas. Okay. So one point here is an alpha, right? Consider the model space of alpha stable parabolic vector bundles. Then this space is crossed by some barriers, right? These barriers are just of the equation that I put before for the non-genericity. These are barriers, these are numerical barriers. These barriers correspond to alpha, such that theoretically there might exist numbers for the degree and the rank of a subbundle that break, that generate an existing strictly semi-stable parabolic vector bundle. That means such that there exists a degree and a rank for which degree plus the sum and sum IF, such that the degree plus the sum over IF the alpha I over the rank is equal to the degree plus the sum over the rank. These are the equations for this alpha. And as the alpha are bounded, then this gives you a finite number of barriers here. So now we start moving with this alpha. And several things can happen. So we must start with an alpha here and be lucky, and when we apply some transformation, we end up in some TD alpha in the same numerical chamber. And then we are sure that these two weights, this T corresponds to an automorphism. Another thing that can happen, though, is that this T crosses one of the barriers, or many barriers. So now what happens? If this T crosses one barrier, when they cross, we don't know a priori if there exists some counterexample. We know for sure that there might exist numerically a subbundle with this degree, this rank, and this structure of subweights that breaks the stability, so that these two barriers are separated by the existence of some parabolic vector bundles. So, if the genus is high enough, we are able to prove that under certain condition on the weights, these barriers essentially, effectively give you a counterexample. At the end, what happens is that we can define some number, m, okay? I'm not going to get into the details. Essentially, rewriting of these equations so that it gives you both directions. And this is going to be called the chamber invariant, the chamber numerical invariant. So what we can do is, as we know exactly which are these barriers numerically, then we can give each of these chamber a number, m, which depends on r, alpha, the d, and some number n, or better said, you can consider this is some number for each array for each partitions of n. Instead of this number, we can consider the array the vector consisting on these numbers. So this lives in some set to the power n for some big n, and this n is bounded. Okay, it's bounded and controlled. So each chamber of each one of these pieces can be associated a number, such that alpha belongs to that chamber if and only if the number is the number of the chamber. So what happens here is that if the genus is high, and high is the some bound for it, through this thing, these bounds can be improved. I'm just giving these like big bounds for the sake of the exposition, so that I don't have to get into technicalities. There are slight improvements of these bounds here, depending on the chamber and so. But let's say for some big bound, then two geometrical chambers are the same if and only if the numerical chambers are the same. That means if the genus is high enough, I can use linear theory to prove that there exists always some element here. And then the result follows. If the genus of the curve is high enough, then the isomorphisms between two modular spaces correspond to natural basic transformations, combination of basic transformations, such that the determinant goes to the other determinant, and the numerical invariant for the chamber is the same as the numerical invariant for the chamber. And with that, in particular, the automorphism group is just the group of basic transformations with the composition of basic transformations which preserve both invariants. As I have a couple of minutes left, let me address briefly what's the difference between this kind of theorem and the two-birational theorem, and more precisely, what happens if I get below these bounds, right? So I said that when you cross one of these lines, if the genus is high enough, you're going to find some counterexample for the semi-stability that realizes that numerical barrier into a geometrical barrier. But the thing that I can take a look at, and that's what I do when we look at two-birational transformations, is how many counterexamples really are. Let me draw it. Say that we have your modular space of parabolic vector bundles over the curve, rank R, weights alpha, and determinant chi. And now you want to consider inside this modular space, there will be you want to consider the transformation to the beta stable, right? And we want to t the beta, so t equal beta equal t alpha, okay? And now we want to consider transformation t that preserves determinant but changes the weights. And then you think, okay, what's the difference between TD alpha stable bundles and alpha stable bundles, right? So the thing is that there's going to be some subsets here, set, where set equals the set of alpha stable but TD alpha unstable, let's see, vector bundles. And now what happens is that if I fix alpha, but I keep growing the genus of G, these things will start to grow. So now I can matter what's the dimension of seed, and what's the codimension of seed inside M, right? So what happens is that if I'm lucky enough for low genus, then the dimension of seed can be 0, or even seed can be empty for low genus. So for each barrier, if I start with low genus, it is possible, and Whether it happens or not is a really difficult geometrical question. It really depends on the geometry of the curve and on the geometry of the space of moduli, on the space of vector bundles, right? Whether you effectively get a seed with an empty seed or not. Right. So what happens is that as I'm starting to hide the dimension of G, the dimension of M and the dimension of seed grow at different rates. So I can paint it this way. Here. I'm going to paint G, and I'm going to paint the dimension of the space. So we know that as G grows, the modular space of vector bundles grows linearly, because it goes like R squared times R squared minus 1 times G minus 1. So this is linear, right? This is the dimension of M. But then what happens is that seed changes a little bit. It will start at some point. It will appear. We don't know why. We don't know when. We know that we don't know this point. But then this will start to grow. Some way, somehow. Maybe not linearly. Maybe something like that. We don't know. But the thing is that we can bound what happens here. We know that it's never going to cross certain lines. So we can give certain bounds in terms of G on the codimension of this variety. So what happens? When we consider two birational elements, what we are doing is saying, if the G is high enough, we can bound for G like this, G greater or equal than 8, we know that whatever happens here, we can give a security space behind the modular space, a band here, such that we know that the dimension of set never crosses it. If we get even higher genus, then we might get some other band corresponding to k equal 3, and so on. So what happens is that if I start getting higher and higher genus, at the end I can make these things happen in some higher and higher codimension. There are bounds. At the end, this grows at different speeds, and if I just keep the genus fixed and I start asking for higher and higher codimension, I'm going to break. But what happens essentially is, I have, just to sum up, I have two ways of crossing this. One is proving that there doesn't exist anything, and this is very difficult, or proving that whether it exists doesn't matter because it will exist with some bounded codimension, and then considering the automorphisms up to the k-birational automorphisms up to that codimension. So just to end up, this I end up, some really small applications of this. The first is that if there's if the weights are concentrated, that means that they are small enough, or they are concentrated, the parameters are small enough so that the stability of the parabolic vector bundle is the same as in the analytic vector bundle. Then what happens is that the modular spaces are the same if and only if the curves are the same, the ranks are the same, and the degrees agree modulo R, are modulo sign. This can also be used in the compact case. That was the other part of the theorem that was missing. So in the compact case, the modular space of vector bundles over a curve agree, are isomorphic, if and only if the curves are the same, the ranks are the same, and the degrees of the vector bundles agree modulo R and up to sign. That means in particular that for modular spaces of vector bundles over a curve, there exist exactly R-half different isomorphism classes of modular spaces. And the same is for the parabolic chamber here. On the other hand, obtaining the Torelli theorem that I mentioned previously unlocks other Torelli theorems that were restricted by the usual assumption of generic way of small weights and coprimality and rank. In this case, these other three modular spaces, the Torelli theorems for these modular spaces, get unlocked immediately when we get the Torelli theorem for higher rank. The modular space of parabolic bundles, there's an existing, these three in fact they are proved by, also by my advisor and by me. With the combination of these theorems with this new proof for the Torelli theorem, gives you also Torelli theorems for the model space of parabolic Higgs bundles of arbitrary rank generic weights, for the Torelli theorem for the model space of parabolic Hodge bundles for arbitrary rank generic weights, and for the parabolic Deligne region, again, for arbitrary rank, and in this case, generic weights satisfying some restraint. And by, finally, this is a little work in progress, future work. With these techniques, you can also compute the automorphism group of the model stacks. And what happens is that when you look at the stack, all these wall crossings really don't matter. You can understand these wall crossings as kind of a change of stability condition, but then in the stack that doesn't matter. So what happens is that when you look at the model space and the model stack in the model space, really everything here simplifies, and you get back to what happens in the 2-birational. You get all automorphisms are the natural transformations. Thank you very much. The Torelli or the?
You have defined new transformation map using Heckle transform. So what about parabolic system?
Oh, you can reinterpret this transformation as a tensor product by some line bundle. Yes. So just tensor.
We know this.
I mean, it's just tensoring with the. I mean, the thing is that the interpretation as Heckle is useful because it allows you to compute things with the determinant and the alpha. But you can reinterpret it, and this is really useful for stability considerations and also for extending it to other model spaces, as tensorization with a particular parabolic line bundle. So then you can do that for Higgs bundles.
Any other question? There is no.
So if you take two parabolic bundles, and you do the Heckle transform, you take the tensor product, do the Heckle transformation, and you first do Heckle transformation of the vector parabolic bundle of both, and then take tensor product. So both will be the same in the same parabolic moduli because of rank condition.
Okay, so let me guess. So you get two parabolic vector bundles of some ranks.
Yeah. Suppose the same rank.
Same rank. Okay. So then you take Heckle transformation here, Heckle transformation here, and now we tensor it.
And also you first do tensor product and then take Heckle.
And take the Heckle transformation of that.
What is the difference?
Oh, between tensoring and Heckle, or Heckle and tensoring. Oh, okay, all right. Yeah. So the difference here is you can understand that by okay. So you can understand that by thinking of the Heckle as a tensor. So you have E dot, and you want to do the Heckle transformation. Then the Heckle of this would be the same as taking this, and then tensor by OX and OX by some weights. And the same with F. Right? So now, if we want to perform the Heckle transformation on the product, this is the same as E dot times F dot times OX dot. So what happens is that here, what are the weights, right? Here the weights are 0 at sort of X, and for X, we're considering here, this is epsilon X, this is epsilon prime X, and here we need to consider a weight which is greater than the first weight of this. So the first weight of this would be the sum of the, so let me do it well, is the first weight of this is the sum of the tensors to sum up to that weight. So I think that you might, I think that you can find it. I think that it should be the same, but the computation is like that. Like once you tensor these two, what you're having is this, tensor these two. The tensor of these two is just O with the sum of these two. So what happens at the end is that if the sum of these two is greater than 1, it's not going to be the same. Because here you are tensoring with something that is weight greater than 1, so in fact you are performing more than one Heckle transformation. It would be a Heckle transformation. Like the tensor of these two would be a Heckle transformation of this. What happens is that maybe here I have to put an L. Because when you perform that, you will perform at least one Heckle transformation on each. So we are performing at least one Heckle transformation on this, but you may be adding more. For example, imagine that this has really small weights, alpha really less than 1, and this has really big weights, like one small weight, and then another big weight. So to perform this Heckle transformation, you need a really small parameter. But to perform a Heckle transformation on the sum, you might need a bigger one. So at the end, you might end up doing more Heckle transformations. Yeah, at the end, you need to make the computation, and I think that you might get that the tensor is it's always Heckle transformation, that's sure, but it might be a higher order Heckle transformation, more than one.
Any other question? Let's thank you.